And we're live. Welcome everyone to MAE 209, Probability and Statistics for Engineering and Science. My name is Richard Kohar, and I hope everyone can hear me okay online. Also, please excuse that it was scheduled for 1:30. YouTube has only allowed me to put in quarter of an hour in, so I could only put it on 1:30 or at 1:45, etc., etc. So, no, we still start at 1:40, and good, excellent, loud and clear. So today's topic is we're finishing up about descriptive statistics, and this is covered 1.3 and section 1.4 in the textbook. On Moodle, you can let me just adjust the encoding. Okay. So hopefully everyone is able to hear everything and see everything. So in this section, in sections 1.3 and 1.4, we're going to be talking about two important characteristics about sets of numbers. And an important characteristic of a set of numbers is its location. In particular, it's its center. So we have our characteristics of the data. So, what are the two main ones that we're interested in when we're talking about descriptive statistics? Well, we can talk about, again, its location or, in particular, its center. So we can talk about, say, location. Okay. Nope, there should be writing on the screen, and if you're not able to see something, maybe try refreshing. Yeah, exactly. Reload and try again. So we can talk about location, or we can talk about the center of the data. And that leads to what we call measures of location. And we have three main types of location for the data. We can have a mean. And usually when they mean that, they're referring to the arithmetic mean. The second one is the median. And the third one is the mode. Sometimes people refer to it as the 3 M's. And another characteristic of a set of numbers is the extent of spread about the center. So let's talk about the spread. And when we talk about this spread, these are measures of variability. So you can have very simple measures of variability, which is the measure of spread. You can think of the first one is the range of the data. We can talk about the sample variance and population variance. You can have then, from that we can have a close relation to it, which is the standard deviation. So you can have this sample deviation, standard deviation. And the population. Remember when we were talking about in the previous lecture when we had the differences between the population and the sample. And there's different formulas for calculating for the standard deviation, if it's a sample or if it's a population, and same thing with the variance. And the last one, I call them quartiles. And in the textbook, they call them fourths. Okay. So on to measures of location. And the first one that we have is the mean. And it's very useful. I can think of it as an average, but we use averages all the time. It gives us a quick way of summarizing data very quickly. It's very simple to calculate. All we do is we sum them up and then we divide by the total number of observations. So let's express this more formally. We can say that the sample mean, and they use X bar. Will we look into other types of means? We could. There's two other types of means that I can think of. So there's the arithmetic mean, but there's also the harmonic mean and the geometric mean. But for now, we're going to, when we talk about in statistics, when we say like a sample mean, we're meaning that it's arithmetic. So we have our observations or our data set, which is x1, x2, and we'll go up to xn. And so it's, like I said, we sum all the observations together and then divide it by the total number of observations that we had, which was n. We're working with a finite set of data. We can also express this using sigma notation, so we can start from 1 to n, all over n. So why do we use the mean? It's simple and easy to calculate. You can do it by hand, but the disadvantage the mean can be easily affected by the presence of even a single outlier. So So what we can do is I should have a running example. So I'm going to keep it on a separate sheet of paper. So let's just switch over to this. You don't have to write all these down because I think these are the same weights. So this is our kind of our running example. And this is the, there's 30, so from 1 to 30. So we have 30 students. Weights. And this is in kilograms. So we can actually, you'll have a calculator. So let's see, I'll have a calculator. And again, the simple way to do it is you punch them all in. Can be a little tedious when we have 30 of them. .3. Excel's sure looking useful right now. It'd be nice if okay, so my total that I get for all these. So I'm just going to make a little. So I know that the total is 1,820.2. And then, so that's the sum. So if we're going to look at the, let me go over here. I'll say that this is the sample mean. Right? And using our summation. Over 30. So again, I'll take that, divide by 30. I'm getting roughly 60.67. Okay. Did everyone else get the same thing as I did? Everyone? No? Yes? Yes? Okay. Yeah, was it 1820.5 or was it 0.2? Okay. Okay. So, just jumping back then to this, to number 2. So again, we have a distinction between the sample and the population. So I gave you the sample mean. For the population mean, So they use a different symbol now, so they'll use a mu of the observations. So instead of it being a sample, what they usually then say is that it's all the possible data, so they use a capital N. For a finite set of all the observations possible. And again, so they'll just say that it's mu is equal to capital N. So yeah, you'll see that it's very similar. All I've done is changed from a small n to a capital N. Okay. Now we move on to the median. And that is the middle value of a sorted, so that's usually from smallest to largest. So a sorted data set. So that's just kind of our intuition. That's our way of remembering it. If we want to be a little bit more mathematical about that, we can say that the sample median and so instead of using a bar, they use a tilde over top of it. They say of ordered observations. And let's say from x1 all the way to xn. I'm using a little letter because I'm using the sample mean or sample median. So if the number of observations is odd, then what you do is the median is the x nth plus 1 over 2 observation. And the issue of it being even, what they do then is they take the average of the two numbers close to each other, and that's it. So they'll pick the middle number and then its neighbor, so the next one over, and then they take the average, so 2. Okay. So with our running example, this can be a little bit challenging because I have 30 numbers. But what I'll do is I have already kind of sorted them on the side here. So I have 56.3, I have 58.4, 58.4, and probably this is the most challenging part of the calculating of the mean, is making sure that the data is sorted from smallest to largest. It's also a little bit more tricky to calculate. As you can see, it's not as simple or straightforward as the arithmetic mean. By the way, can anyone tell me what the quickest sort is then for this? having an array of numbers, since we've done, there might be some I think there's one computer scientist at least. Can anyone tell me what that would be? What kind of sorts do you recall from 101? Does anyone remember their sorts from 101? Yes, quick sort. Yep. Quick sort's good. Bubble sort. So bubble sort has a complexity of n squared. And for Neil, who said quick sort, or Eric, who said quick sort, do you know what the complexity is for bubble sort? Or quick sort? That's what I meant to say. I think in 101 they taught bubble. And then if you're into the second year courses, you would have seen more complex, more advanced sorting algorithms. So I think with quick sort or with merge sort, they're in n log n. And of course, people are Googling, so make sure that you are checking fact. Yes, n log n. Okay. So yes, you would use some sort of algorithm. You could sort this very quickly. So now that I've sorted it, and the other nice thing too is there's numbers from 1 to 30. So for our sample median, what I do then is I know that it's 1 through 30, so there's 30 observations, which means that I'm going to be in the even case. So I need to find the n is 30 over 2, which is then 15, right? So it would be observation 15 and 16 over 2. So observation 15 and 16 over 2. So that's 60.8 plus 60.9 all over 2. And I'm getting 60.85. Now, so the advantages with using the median, again, you saw that. Less prone to outliers affecting it, because we're basically just looking at the middle of it. But the disadvantage it's more complex to calculate. You know, if we're looking at the complexity, the sample mean just takes us once to go through, so it's just n additions to go through it. We're going through it linearly. And to get to the median, we have to actually sort all of them. And the best case for that is n log n. So it's more complex to calculate for sure. Okay. Just a just as a side note, there's some people who prefer using a trimmed median or a trim mean. And that's kind of a compromise between the mean and the median. What they do, so I'll just say that it's a compromise. So what they do is say, for example, for a 10% trimmed mean, what they would do is they calculate it by eliminating the smallest 10%. So they'll take the data and just throw the bottom 10% out, and the largest 10%. And then calculate the mean. Or then, yeah. Okay. Perfect. And the last one that we'll do the mode. So that's the value that appears the most in the data. I'm not sure what that means. Okay. I'm going to add a moderator for this. Excellent. Okay. So then going back to our example, the mode is the value that appears the most in the data set. And if I scan through this, there's a couple of times where I see here 58.4, 59. I see also 61.4. So this is quite hard for me. Using that definition, we see 58.4. I also see 59. 61.4. $61.9. And remember last time we were talking about that there can be such thing as more than one mode. This is multimodal. Any questions so far? Mean, median, mode. Okay, let's switch back to page 3 here. So here's some measures of variability now. That's a good question. If it's negatively or positively skewed. How did we do that before? If we flip back to our previous pages. Previous lecture, we talked about negatively and positively skewed. How do you think we would handle that? We were doing it visually. Looking at a histogram, yes. You can look at a histogram, or perhaps maybe looking at a dot plot could help. And then from there, you would be able to determine if or visually determine if it's negatively or positively skewed. Good. Yes, graphing it. Okay, so with the range of the data, it's usually that we take the maximum and we subtract the minimum. Now, because we have this all ordered, this is quite useful because I can quickly look at this. I can see that the minimum is 56.3. The maximum, looking at the end here, is 65.7. So then the range is equal to 65.7 minus the minimum. Putting that in. .4. Okay. So that's an easy way of looking at the variability, is by looking at the spread, how much it is from the minimum to the maximum, and we see there's a range of 9.4 kilograms. What's the next one? We can do... Okay, so we're going to talk about variance. And what the variance is it's the average squared distance from each data point to the mean. So when we have the sample variance, so we can have the sample variance, and we can also have the population variance. So with the population, we tend to use Greek letters. So we were using mu for the mean, and we're going to use sigma to mean for the variance. We use sigma squared. And that is equal to, again, we're going to take, it's the square of the distances. So it's the data point from the mean. So in this case, it's the population mean. So it's mu. It's the squared and the average. So we're going to sum all those distances from the population mean. We're going to square it, sum them all up, and we're going to divide by the number of total observations. Oops. 2n. There we go. So again, mu, that's our population mean. And so over here, it's very similar. So we've been using letters, so we can use s. We're going to use s squared. And again, very similar. We're going to take the data point, and we're going to take the distance from the mean. In this case, it's the sample mean. It's squared. We're going to sum them all up because we're going to take the average. And this is where it is a bit odd. It's not n, but n minus 1. Why n minus 1? I'll have to say we'll learn hopefully this later in the course. But the reason for it is to have an unbiased estimator. So that's the difference between the sample and the population variance, is just the n minus 1 in the denominator. So that's something to kind of keep note. Maybe I'll even put a little highlighter bit there. Kind of making that difference between the sample and the variance. Okay. Now another formula or way of expressing this is I can express this as mu squared is equal to I'm going to take 1 over n minus mu squared. Now the reason for that here's number 4, page 4. So I'll say see page 4. So here's the proof. So what I can do is I start out with the summation. Okay. And I'm going to just rewrite this a little nicer. So I got 1 over n just a little bit of a different way of writing it. So I can do this. The next thing that I can do is I'm going to expand this out. I have a squared here. So I can do 1 over n so this is xi squared minus 2xi mu plus mu squared. So I'm just squared this, right? Remember, don't start distributing. It's not xi squared minus mu squared. Remember that it's got to be right. Then the next thing that I can do is I can apply the summation to each term. The summation is a linear operator, so I'm going to apply the summation to each of these terms. I noticed that the 2 mu doesn't affect the sum here. We don't need to worry about that. So I can actually pull that out. So I'm left with 2 mu. I have the summation. And same thing with this one. I have mu squared, but it's a constant, so it's going to be summed n times. So it's n times mu squared. Maybe at this point, what I do now is I'll distribute the 1 over n to each of these terms. So I have 1 over n times the sum. Then I'll have 2 mu over n plus I have n over mu squared over n. So these n's cancel. I also have this, which also then simplifies down to just mu. So I'm left with 1 over n so I have 2 mu squared plus mu 2 minus 1, or 2 minus 2 plus 1 is just 1 minus 1, so it's minus. So, which matches what we have for over here. So it's a different way of calculating it. And similarly, here's an alternative formula for the sample variance. Okay. The next one that we have is then the sample standard deviation. So instead of using the average squared distance, what we can do then is we can think of this as the average positive distance from each data point. So one way to make things that are positive is to square and then take the square root of it. So the sample standard deviation is simply s, and we take the square root of s squared. And similarly for the population, standard deviation, again, because it's population, we prefer using Greek letters. It's sigma, and we just take the square root of it. So if we wanted to look at the data, if we wanted to calculate the sample variance, that's s squared equals what we would have to do then is we need to square each of these, sum it, then I would need to take the sum of all of these, square it, and then divide by n, and then n minus 1. Now, that can be a little tedious. What I can tell you is that the sum, you would have to, but we've run out of time. So what we'll do is we will continue this in the next lecture for lecture 4. Thank you everyone for tuning in, and have a look at some of the questions now that are posted on Moodle, and send me an email if you have any questions at my RMC account. Thank you everyone for tuning in, and have a great day.